All right, I'm live, I think. Hi. Maggie's here. Okay, Lillian's here. Okay, hi, Ann-Sophie. Could one of you guys post in your class chat as a reminder that this is happening in case people are on WhatsApp and are not aware? Bella, hi. That would be helpful. Please. BRB. I'm supposed to know what that means? What does BRB mean, Ben? What? You don't know what it means either. Okay. Hi, Aiden. Hi, Matilda. Be right back. So Evelyn's here. Good. Thank you. Oh, be right back. Oh, cool. Thank you. Thank you. Sweet. Dankeschön. Cool. Okay, we have now 257 of you here. That's a little bit low, I would say, but we'll get started pretty soon. Thank you for posting on your WhatsApp group. Okay. Eddie's here. Lola's here. That's better. We're moving in the right direction. Okay, good. We'll get started. Hi, Antonin. We'll get started in just a minute. I just want to, first of all, we'll keep for this now. Just want to encourage you guys to hang in there, do your thing. Even better, do better than your normal thing, and do a good job with what you can do to keep this education thing going. I already had that little speech with you. I thought you guys really kind of recovered a little bit on your homework scores as a group. So I thought that was exciting. You guys are still in last place out of 6 teams. I don't know if you saw that, but you've improved quite a bit, and now you're actually in striking distance of 7th grade, the 7th grade group. And you guys can do this. You guys can get some homework in, encourage each other to turn things in and get better. The other thing is I did write people about the lab reports. Those are still due, and I will grade those, but I first was struggling. Hi, Jolfi. I was struggling to make sure I had pretty much most of them who are going to turn it in turned in before I start grading and then entering and pushing back and then kind of going back all over again. Hi, Benji. Good. So please, both of those, there's still labs that are not turned in, and the homework assignments, get a little attitude going as a team and see if you can knock these out. The assignments themselves are really rather short, especially, hey, I mean, yes, on the labs, I only wrote the people who were missing labs. So if you didn't get an email from me about labs, then you have everything turned in. Okay, so it is now 04. I have the following people listed as not being here right now. Yes, I'm grading the homework. I'm grading it relatively quickly, looking for certain things. I'm not scoring everything, but I am looking for completion generally, and then maybe looking at a couple of the questions to make sure that you guys are actually doing the work. And I have turned scores back for 1 and 2. So Khalil is not here. Sky is not here. Manny is not here. Jonah is not here. Adrian, hi Khalil. Adrian is not here. Okay. All right, good. We'll get started. We only have a few minutes, and I kind of thought about what I wanted to do today in terms of using this time effectively. And what I decided was I was going to look at the topic of hang on, here's red. This is the best one I have. The topic is wave speeds and large numbers. So, and the reason I'm doing that is because a couple things where there are two really big speeds that we're dealing with when we're talking about the speeds of waves traveling. Hi, Adrian. There are two really big speeds we're talking about, specifically the speed of sound, which is about 343 meters per second. Oh, shoot, I could have asked you about that. And then we have the speed of light, which is also called c, speed of light in air or vacuum, which is 3 times 10 to the 8 meters per second. But a maybe more useful way of writing that is 300,000 kilometers per second. That's okay, Adriana. I'm checking you off as here. So looking at this C, yes, correct. Looking at those numbers, they both have, they both are very big, okay? And the problem with humans is that once you get to really large numbers, it's just really big, okay? Let me illustrate that to you. You guys have a pretty good idea of what 100 euros are, and I think you have a pretty good idea of 1,000 euros. Because that's kind of what the newest iPhone costs, for example. You might also have a pretty good idea what 100,000 euros is, or even 1,000,000 euros. 100,000 euros might be the cost of a really fancy luxury car, or so. And 1,000,000 euros might be what you're dropping on a really nice house in Berlin, for example. So you get kind of an idea of what those numbers mean. But when you get even bigger than that, if you're talking about 1,000,000,000 euros or 1,000,000,000,000 euros, things kind of shut down. Okay, and that's a little bit of a problem because I think politicians kind of abuse that a little bit because when they say something like, "Oh, why don't we put 1.8 trillion dollars into the economy for this Corona crisis?" Most Americans are like, "Well, that sounds like enough." But it's very unclear that anybody has a good idea of how much money that is. So before we go here, I actually wanted to look at that number because it's in the news, and today in Congress they're going to be passing, hopefully, a bill to move that forward and actually put 1.8 trillion dollars into the system. So that's the Corona rescue amount, and it's 1.8 trillion dollars. Okay, and like I said, 1,000,000 maybe you're still able to somehow grasp, but 1,000,000,000, that's really difficult, and 1,000,000,000,000 is absurdly impossible, basically, because it's so large. And just to, I mean, we could write it out, but I don't think that'll help. I will do it though. Okay. So there's the number, 1.8 trillion dollars. And again, once you get past a few zeros, you're like, well, I don't know. That seems just like a lot. And if we added 3 zeros, you'd still be like, well, that's a lot. And if we get rid of those, it's like, wow, that's just a lot as well. So how to distinguish the difference? So the trick is with that kind of number is to get a better feeling for the number by putting it to a human scale. Okay. And for example, for this kind of number where we're talking about the American government spending a certain amount of money, it's a good idea to put it in perspective by comparing it to how many people there are in the United States. Okay. And I think in general, that's not a bad idea about any kind of political discussion. If you're talking about buying an aircraft carrier or 10, what the heck? They're on discount. Let's buy 50. I don't care. Okay, or you're putting money into the economy and you come up with absurdly large numbers like 1.8 trillion dollars. And why don't we say 5.7 trillion? Why don't we say 129 gagillion? I don't know. Okay, is to put it in context by comparing it to the number of people in the United States. So, as you might know, we have about 330 million Americans. Okay, and if you put it in that context of 1.8 trillion per 330 million people, you suddenly come up with a number that you can have a better conversation about. Now, I don't know if you've already put that in your calculator. I'm going to put that in my calculator just to see what happens. Now, to make it easier, nope, I'm not going to make it easier because it's going to confuse people. So let me look at the number. So 1,800,000,000. Oh crap, it doesn't even fit in the calculator. 1.836912 E12 divided by 330, 123. And I get a number that says, I don't know if you can see it, $5,454 per American. Okay. So, wow. Now we're getting to a point where suddenly, technically it rounds up to 55 per, where suddenly that number that just a second ago seemed extremely abstract. Yeah, you can use scientific notation, correct, Antonin. So we come now to a number, $5,455 per American, where that number comes into perspective, because people can put this number in perspective, especially if they think about it for their family. So, okay, so that number means that would be about $22,000 for a family of four. $22,000 for a family of four. That is an unbelievable amount of money in terms of the size of this bill. And it's really a better way of thinking about that number by putting it basically into a human scale than just talking about 1.8 trillion, which is like, what does that even mean? So it's always a good idea to kind of scale things down like that in order to get a better way of looking at it. So if you're talking about anything really, you could even talk about the number of corona cases in the country. Those numbers are big, but if you compare it to the population to get a percentage, then that's really a better way of looking at it. And what does it mean that, you know, America has so and so many cases compared to Germany, and how many people live there, and so on. Okay, good. So this is kind of the intro to the idea of large numbers, and let's take that and actually use that concept when we're talking about waves. So first things first, when you have sound and light, you guys actually have, you should have in your mind a little trick to figure out how to think about the speed of sound compared to the speed of light. And if that is referring to a rule where you can figure out how far away lightning strikes when you're out and about, say you're on a hike and there's lightning, and you hear the lightning and you see the lightning. Hi, Jonah. Thank you for coming. So when you look at this, what's that rule? Like if I see the lightning, and then I wait, and then I hear the lightning, and I counted to 4. Do you guys know how far away the lightning struck? Silence. So that was a question. So I've noticed that I counted to 4 seconds after. Oh, there we go. Good. About 1.2 kilometers. Okay. Let's think about this. Good. I'm glad you guys are thinking about it. And let's think about what it means to see the lightning first of all. And then what it means to hear the lightning. Okay, so let's take a look at the speed of light, which is of course us seeing the lightning. Sorry. This speed is so fast, okay, that for us to see, hang on, we're getting there. Just a minute. This number is so big that we basically see lightning immediately. What I mean by that is on a human scale, when lightning occurs, and let's say it's a few kilometers away, it's going to take such a short time compared to the speed, maybe 100,000th of a second, 10 microseconds, that basically takes no time for the light to get to us. Okay. However, when we see the lightning, it takes more time for the lightning's sound to come to us, the thunder and lightning. Well, thunder is just the sound of the lightning, right? This lightning's sound, the thunder, takes time to come to us because this speed is not negligible compared to human. We're getting there. Compared to a human scale. And what we're going to do is we're going to take this number and we're going to approximate it as a third of a kilometer. That's very close. 333 meters per second. 333 meters per second would be a third of a kilometer per second. So what does that mean in terms of if we're out for a hike? If we're out for a hike and we see the lightning and we count the seconds until the sound comes to us, when we get to 3, that means it's more than a kilometer away because this would be a third, 2/3, 3/3. Okay? And then when we count to 4 seconds, it will be 4 times a third, or 1.333 about. It's actually closer to a little bit more than that, but it's very close to that answer and close enough for safety purposes. What we mean by that, if it's this close, a little less than 1 kilometer, a little more than 1 kilometer, it can get to us pretty fast. Okay? If there's a bigger time difference, maybe 5, 6, or 7 seconds, then it's definitely still quite a ways away. So kind of a rule of thumb, that the distance is equal to the time divided by 3 in kilometers. So if you count the seconds that it takes, well, I kind of cut through this here a little bit. So if you count the time in seconds and you divide by 3, then you get a pretty good idea of how far away the lightning is. And this should be something you should be using if you're out hiking, for example, or you go mountain climbing or whatever. You have outside, even if you're outside playing soccer at the Gleisdreieck or whatever, and then there's suddenly lightning. You go, how close is it? Is it like right here? Do we have to seek shelter right now, or can we just casually walk to the S-Bahn? What's our situation? Okay, so this is a very good rule to have in life in terms of being able to deal with how to figure out how far away lightning is. And if it's close, if it's like 5 seconds or closer, less than 6 seconds, let's say that, less than 2 kilometers, I think is definitely something where you should be concerned because it can get to you pretty quick and you can be in trouble. So if it's shorter than that, seek shelter. If it's closer than 3, then seek shelter now, like, whatever. If it's like within 1 second, you're just a few hundred meters away, it could hit where you are. Okay, so that's a general guideline for that, and I think that's a good thing to have in mind. Now, let's come though back. So this distance right here is the sound speed, and a third of a kilometer per second is a good guideline for that. Airplanes, for example, jet airplanes travel very close to the speed of sound. So they also travel about a third of a kilometer per second, which is a good guideline for you to have in mind as to how far a jet plane travels. Okay, so a jet plane travels about 1,000 kilometers per hour. okay? And that means it's covering a kilometer every 3.6 seconds. Trees are not shelter. That's correct. Yes, trees are not shelter. So look for an underpass. T over 3 is correct. So take the time in seconds, divide by 3, and then multiply. Then you get your answer in kilometers. So count your count your 1 Mississippi, 2 Mississippi, 3 Mississippi, 4, or 21, 22, how the Germans do it, 23, okay? And then you have the time, and then you have the distance. Okay, now let's do the same thing here. We have a different situation here with the speed of light. The speed of light is completely on a non-human scale. The 343 meters per second, that's something you can at least picture. You can be like, well, 343 meters, that's like once around a lap of the Sportplatz. That's 400 meters. I have a feeling for what that distance is. And if you tell me you went all around the lap in 1 second, I'd be like, whoa, I can picture that. That's incredibly fast. I need like 1 or 2 minutes to go around the lap, depending on how good of an athlete I am. And you did it in 1 second. That's unbelievable. But at least it's still physically for you to comprehend how big that number is. This number, on the other hand, is so insanely large that you cannot get a decent understanding of what that means. So that's why we have to actually take this number, and instead of talking about it directly, we're going to use not a crutch, but we're going to use something that humanizes that. Okay, let me explain. The distance to the moon is 384,000 kilometers, and the distance to the sun is 150 million kilometers. Okay, so if we look at these two numbers, we would be like, holy cow, those numbers are insanely large, but they both simply seem insanely large. This number is so big that we don't have a good idea of what that means. So if we take a look at the speed of light, they can work together to make each other better to understand. So we have 384,000 kilometers. If light travels from the moon, now you've seen the moon, obviously. If you see the moon, that light has been traveling this distance towards us, 384,000 kilometers, at a speed of 300,000 kilometers per second. So let's figure out the time that is. Time from the moon. So we're just going to take this speed, this distance, and divide it by 300,000. Okay, so if we type 384,000 into our calculator, divide by 300,000 kilometers per second, we get out that the moon light takes about 1.3 seconds to come to us. Okay, we can express this differently. So first of all, that time period is something that you can be like 1 Mississippi. So kind of like when you see lightning and then you hear the lightning. That can be 1 second, 2 seconds, 3 seconds. It's a similar delay for the moon. So the moon, actually, when you see it, that light has been traveling for 1.3 seconds. No, light does not lose speed when it's reflected or diffracted. So 1.3 seconds is the time it takes to get to us. We can also use this over here, and instead of saying 384,000 kilometers, we can now say that the distance to the moon is 1.3 light seconds. So instead of saying this in humongously large number that we really don't understand, we can say instead the moon is 1.3 light seconds away, and now we've humanized it. We can understand that distance better because we can understand 1.3 seconds. 1 Mississippi. They're a little bit more. There you go. So 1.3 light seconds is the distance to the moon. Let's apply that idea down here to the distance to the sun, and then we'll get finally a better idea of how far these two things are away from us comparatively. kind of like thinking about that $1.8 trillion, now we can kind of like, oh, okay, I get a better idea of how big that number is. So we have 150 million kilometers, and we can figure out how long light takes, again, from the sun to get to us by taking this distance and distance dividing it by the speed, 300,000. Good. So the time is the distance divided by v, shown up. Okay, so here it is. So for our example here, for the moon, okay, we used for the time to the moon, from the moon, the distance from the moon divided by the speed. So that would be 384,000 kilometers divided by the speed, which is 300,000 kilometers per second. And if we punch that in our calculator, v light, that's correct. So this is the speed of light. So we have 384,000 divided by 300,000. And I get 1.28 seconds or 1.3 seconds. I just rounded it to 1.3. Okay? You guys cool? Makes sense? Yes, v is the speed of light. So this is the speed we're talking about. We can replace v with c, and then we can get the time for the light to get to us from the moon. Okay? I'm going to take that as a yes. Does that make sense?
No.
Yes. Okay, good. So we can repeat the process with the sun. And we can say, okay, we have 150 million kilometers as the distance to the sun. And we can therefore find the time it takes the light to come to us by taking that distance, 150 million, dividing it by 300,000 kilometers per second. 150 million divided by 300,000 kilometers per second. And it cancels out nicely because 15 divided by 3 is 5. And we get out 500, whoopsie. We get out 500 seconds. Okay? 500 seconds is the time. Now, we do not normally talk that way because if you ask somebody, oh, how long did your 3 kilometer, wait, 3 kilometer, that's too fast. 8 minutes. It could be actually, you could actually run that. How long did your run take? And the person says 500 seconds. They'd be like, what? Or if you make hard-boiled eggs, how long should you leave them in there? 500 seconds. You'd be like, no, that's not the way normal people talk. We don't talk about seconds when it's more than 60, because at that point we talk about minutes. So we look at 500 seconds and we say, it's about 8 minutes. Okay, so 8 minutes is the time for the light to get to the Earth from the sun. 8 minutes. And that means, of course, to be more precise, it's 8.3, but that's fine. So what that means is that when we look at this distance, 150 million kilometers, which is incredibly difficult to understand, we can now rephrase that as 8 light minutes. So the distance to the sun is 8 light minutes, about 8.3. The distance to the moon is about 1 light second or 1.3 light seconds. But even just saying 1 is a good ballpark and a good, pretty accurate number. And then you can also compare it to 8 light minutes, and that makes sense. We're coming to the end here, but I think the key thing for you to keep in mind, those numbers are very scalable and get an idea for that. Keep in mind that the closest star that's not our sun is over a light year away. Over a light year. And a light year is 31 million seconds. So, wow, that is really, really far. So the nearest nearest star, our sun, to us, of course, 8 light minutes. The nearest next star is over a light year away. Okay, so we're at the end of our time at 9:30. I hope you have a better idea of how to deal with large numbers in terms of even things like the corona bill, but also have a better idea of how to understand large speeds and large distances. Okay, so yes, it is Proxima Centauri is the closest star to us. Okay, so oh, for the FET labs, I will send a reminder by that as well. I just need to make sure. I want to make sure that you guys can use it. So mark it as done if you've looked at it. It works, and then just mark the assignment as done. And I will send a reminder about the FET lab simulations as well, and that's due by Monday. Okay. Otherwise, please do some more of the homework. Would really appreciate to see a higher percentage of you guys complete it. Encourage each other, and maybe hunt people down who don't have theirs turned in, or help them. Either way is fine. Look at positive, negative, whichever it is, and see if you guys can get that stuff. No, you do not have to do anything on the FET lab simulation yet. I will send you out an assignment, but before I do that, I wanted to make sure that we're not going to get held up on technical issues. So I want to make sure that all of you are able to open it and use it. Then just as long as you've got in there, you've seen it, it's working, you haven't done anything with it, that's cool. Just so you've done it, open it. Okay, good. We are past our time by a minute, and have a good weekend. It actually is the weekend coming up. And hang in there, and go team.